This diagram maps a standard SSH connection and its core assumption. Servers are protected targets requiring hardening, while clients are secure originators. That model is now inverted. Vulnerability CVE-2026-55200 allows malicious servers to weaponize the SSH protocol, firing attacks directly back at the connecting client. The flaw resides in libssh2, a core client-side library used by millions of systems worldwide to manage secure shell connections. Exploiting this library, a malicious server achieves remote code execution on the connecting client machine, gaining total control over the system that initiated the connection. The attack requires zero authentication. It triggers before prompting for usernames, passwords, or cryptographic SSH keys. Robust defenses like 4096-bit key pairs or multi-factor authentication are entirely bypassed. To understand why these defenses fail, we must examine a memory allocation failure in the transport layer and trace its impact across automated infrastructure. Connecting to an unverified server using libssh2 grants that malicious host a direct, unobstructed path straight into the client's internal memory architecture. This sequence diagram outlines the chronological phases of a standard SSH connection: the TCP handshake, transport layer setup, authentication, and finally channel multiplexing. Most SSH-based attacks, like credential brute forcing, target the authentication phase. This vulnerability targets an earlier phase. The flaw sits inside SSH2 transport read, executing during transport layer setup. Because the exploit triggers here, later connection stages are never reached. The malicious server infects the client within the first few seconds of the handshake. This happens before the software performs standard server identity validation. Credential policies are not part of the equation because the exploit executes beneath the authentication layer. The role of SSH2_transport_read is to read incoming SSH packets and validate their size by checking a header value called packet length. While libssh2 defines an upper boundary for these packets, it fails to strictly enforce that limit within the code during this specific check. This horizontal array represents a 32-bit register, which is used to store the packet length variable. A 32-bit integer has a fixed capacity of just under 4 gigabytes. The attacker sends a crafted packet approaching this limit, saturating the register. Mathematical operations then push the integer past its maximum. It overflows, wrapping the value back to a tiny number. The system accepts this wrapped-around tiny value as the legitimate size for the incoming packet. By utilizing the rules of memory architecture, the attacker tricks the system into believing a massive payload is actually microscopic. This memory map shows the result. Using that erroneous tiny value, the client allocates a small block of heap space to store the data. This tiny allocation sits adjacent to critical execution flow pointers. The function attempts to write the actual, massive payload into this tiny space. The payload causes an out-of-bounds write, spilling over boundaries and corrupting the surrounding memory spaces. The overflowing data overwrites the adjacent execution pointers, replacing the application's original instructions with data controlled by the attacker. Hijacking these pointers allows the attacker to dictate the system's next CPU instruction. This leads to full remote code execution, operating within the privileges of the client application. A missing boundary check in the transport header allows the attacker to bypass encryption and gain total system compromise. The release of public proof-of-concept exploit code has moved this threat from a theoretical risk to an actionable danger across 3 network topologies. In Scenario 1, SSH server honeypots, malicious servers are designed to trap and infect automated systems attempting outbound connections. Scenario 2 is supply chain compromise, breaching a legitimate server to weaponize it, infecting every connecting client. In a DevOps environment, a compromised deployment target cascades backward, infecting the enterprise build server. Scenario 3 is man in the middle, intercepting traffic on an insecure network, infecting the client during handshake, then silently forwarding the connection. Because automated systems cannot inherently distinguish between these topologies, every outbound SSH request becomes a risk to the internal system. This raises the question of who is actually exposed. libssh2 is a silent dependency. Many system administrators are unaware their software relies on it. This dependency tree shows why. Major data transfer tools like curl rely on libssh2 for SCP and SFTP protocols. Through curl, the vulnerability extends into GitLab Actions, backup utilities, and IoT firmware. CI/CD pipelines and IoT devices are particularly high-value targets for this exploit. These systems often make thousands of automated outbound connections daily without human oversight or manual verification. Administrators can identify their exposure by using the LDD and LDconfig commands to inspect tools like curl and confirm if libssh2 is actively linked. Systems running libssh2 version 1.11.1 or lower must be updated to version 1.11.2 or higher immediately. For legacy systems where updates are not feasible, mitigation involves routing outbound SSH connections through an updated proxy and enforcing strict known host validations. Effective defense in depth involves treating the wider internet as malicious infrastructure, capable of hunting the internal systems that connect to it.